Okay, so welcome everybody, and I'm very pleased to be able to present chair the next session with the speaker Spencer Thomas from MPL, who will be talking about metrology and uncertainty in machine learning.
Thanks very much, Catherine, for the introduction. So everyone, I'm going to talk to you about this topic, metrology and uncertainty in machine learning. Just a very brief overview. So I'm going to talk about some considerations of both the data and the model in machine learning problems, and where metrology kind of fits in with that in the machine learning framework, and then just give some examples of how they've been used, some tools that are available, and some real kind of world cases to go through. So models and data are both important. The data is as important as the model. Quite often you will see people present the results of their model, and then the success or failure is attributed to the model that was selected, or the way it was set up. But there's aspects of the simplicity of the model, the complexity of it in terms of both the data available for training and things like this. And by problems, I mean a kind of collective term for uncertainty, quality, density, dimensionality, all of these kind of concepts. So just kind of catching all those things with the term problems. But there's also problems associated with the data in terms of the quality of data is fairly well considered, and uncertainties in the data itself. But that also extends to the labels in the data. So for classification problems, you have your data points, your X, and your labels Y. They both potentially have uncertainty associated with them. I'll go into a little bit more detail about that in the next couple of slides. But then there's also problems with potentially the combination of the data and the model. They both might be perfectly fine in their given contexts. The data may be very well collected and very well standardized. The model may be suitable for those kind of tasks, but for some reason, combining the two of them, there are still some issues in there, and that might be just to uncertainty propagation through the model itself, because of how they're fitting together, or limitations in the training set. So an example of that is if you say have a data set that is not fully capturing the problem you're trying to apply it to, or there are instances in your test set that are outside of your training set, that will impact obviously in the performance of your model. So in most cases, you can't expect the model to know what it hasn't seen before. There are obviously some exceptions to that, but yeah, there's some cases I'll show where this has happened. And so we need to consider all of these things when we evaluate the performance of some machine learning. So it's not just the model and it's not just the data, it's both of them separately and together. So problems with the model, I won't dwell too much on this because Stefan gave quite a nice talk yesterday that covers some of these issues in terms of overfitting or underfitting and overparameterization. And these kind of problems are very well understood by this community and this audience, so I'm not going to dwell too much on these kind of concepts. But obviously, if anyone has questions, please ask. And there's obviously a role of regularization in a lot of this to help overfitting problems specifically, and there's some more details I go into with this. But for now, this kind of catches all of the problems with the model, I would say. I'm sure many of you are familiar with. Problems with the data, so I kind of mentioned we have kind of uncertainties linked with this. So for things like unsupervised tasks where we have some data X and we want to obtain a mapping from our usually a high dimensional data to some embedded space, typically a low dimension. That's not always the case, but this is typically what we want to do in unsupervised tasks. So we want to obtain this mapping, but this observed data X is actually a combination of the true data, the real data, and then some uncertainty associated with it. and depending on the context that comes from, this epsilon might be very well understood, it might be poorly understood, it might have multiple sources that relate to the instrumentation, the statistical properties of things, and many other aspects. And there's also an interesting question on the absolute quantitation of this value, or even this value, depending on how it was obtained. That's slightly outside of the scope of what I'm going to talk about now, but it's something to consider, that particularly in experimental science, these are not always well, absolutely quantitative, and so that brings an interesting question in terms of classification and machine learning tasks. So I think these kind of concepts have been well covered in some of these talks over the last couple of days, and will in the remaining talks. And the dimensionality of this data has an impact in what you can do in this embedded space, and how well this mapping works. For instance, if the orders of magnitude are very, very different, this can make the task very easy for some problems, or very, very challenging for others, depending on the kind of heterogeneity and sparsity of the data, and the amount of it you have. But this also extends to some supervised tasks, so where you have pairs of data and labels, where you want to find a function that approximates the label based on this input data X, usually solved by a minimization task. But these labels potentially have an uncertainty associated with them as well, and this could be in terms of the actual label given, in terms of what category it falls into, what the physical continuous value, what the uncertainty is on that. But it can comprise other things, such as the complexity of the label. So that depends on the context. And if you say have an imaging classification task, the content of that image might impact on this. So if you're classifying the foreground and the background, and you have multiple components in it, then this may not be so straightforward. And so here's an example of where this labeling issue can really come into play. So this is a slide taken from some collaborators of mine at the University of Surrey. So this is a digital pathology slide. So this is a digital microscope image of tissue sections from an animal that have been stained. And for those not familiar with these kind of tasks, so these images are used by pathologists to diagnose healthy and diseased tissue, and it's used quite a lot in machine because it's an imagification task. But there are lots of kind of metrology concepts to think about in this. So in terms of what actually is a task, is this a binary task of is there cancer or not cancer? And are we taking this whole tissue section, regions of it, or are we interested in location? So if it's a binary classification task, then you have issues around how much of the positive class do you need to do this in a statistically significant way. If you're interested in location, then the boundary of this becomes very, very important, as you can see here from these zoom ins. These are annotated by expert pathologists on where the boundary is between cancerous and normal tissue. These boundaries are very complex themselves, and so if you want an algorithm to trace this out, then that's quite a challenging task. But also the absolute location of this is potentially not known. So this is annotated by a pathologist, but different pathologists may have different perspectives on where this boundary actually lies, whether there's actually a grading between these two tissues. Is it a definite boundary between the two, or is there some kind of gradient between them? And so all of these things fit into how complex this task is, and therefore how we approach it from a metrology point of view. And the uncertainties in this also include the actual uncertainties in the data itself. So this itself is an experimentally acquired bit of data, so that has all the kind of typical uncertainties associated with that in terms of calibration of the instrument and the staining here. And for this context, there's also uncertainties or heterogeneities, at least in the data itself, the biology, how this was acquired. So these become really, really complex problems when you start to think about these level of details of the problem, rather than just a binary classification task here. So some problems with the combination of the data. So we've seen a lot of GANs being used recently, and Goodfellow's paper kind of sparked a lot of this. Looking at this image here kind of shows this quite nicely, where this is classified as a panda fairly confidently, adding some small amount of noise, then completely changes the output to a very, very confident misclassification. Now, if this level of noise is small enough that it's probably within the realms of acceptance for a given problem, then this is a case of the data and the model not combining very well, and these errors kind of propagating through and then causing this kind of catastrophic failure. And GANs are very good at exploiting this, because they can learn these differences to make to cause this failure. In the same way the deep networks can learn these features from the images. This paper here showed that even just inverting the color of the images, either binary images or grayed images, gives you misclassification of these probably more simpler problems. And so you would kind of want your algorithms to be more robust to perturbations than perhaps is here. So this is kind of a little bit of the data being outside of the training data being outside of the scope for what you're then applying it to. So I'm presuming this is MNIST here, that these kind of images weren't seen in the training set. So I think a bit of care needs to be taken in terms of how we're training and then how we're using our models. And again, this kind of links to the combination of model and data is dependent on the task in terms of how successful that will work. So this is an algorithm called Pulse that is very good at reconstructing blurred images. So you can see here that these images are very, very low resolution, and this algorithm here is very good at restoring the high resolution original image. It was downbin to give this. So very, very powerful algorithm, very successful. But there have been some fairly publicized issues with this data in terms of the sample data being used. So here we've got a blurred picture of Barack Obama that has been reconstructed to a white man, and then the same thing with Lucy Liu. And so this has caused a lot of debate in terms of the bias in machine learning and these kind of problems. I don't really want to get into any of that in here, but the data set used to train this algorithm was not diverse enough for these kind of applications. And this is an example of how a data set was used with a very, very high percentage of white faces, and then the model is essentially only able to reconstruct white faces, and so you have these kind of issues that arise, and that in itself is indicative of wider problems that aren't really in the scope of this talk, but things to consider. This is quite a prominent point at the moment, these kind of biases, and obviously this extends to other less politically sensitive topics too. So complexity is another thing. So the models tend to be can be fairly complex to solve some of these problems, but they don't always have to be. And this was a nice paper that showed that stochastic gradient descent actually learns very, very simple models initially, and then increases the complexity to solve the problem kind of as is needed. And that kind of brings an interesting question in terms of, you know, how complex do our models need to be, or how simple can we get away with? And so this is a very, very simple example I'm going to show of how you can get relatively good performance with a very, very stupid model, if you like. So everyone I take it is familiar with the MNIST dataset. And if you visualize this with TSNE, you get these very nice clusters. You get some data points that kind of overlap, but broadly you get a nice separation of the different images. So if we take each image and stack it pixel-wise, so now we have the stacked pixels for all of our training instances for a given digit. So this is all the same digit here. We have the stacked pixels here, and then our training instances. So viewing kind of all the zeros and all the ones and all the twos as a single image, we can take a histogram of these intensities here, and we can use this to develop a kind of an underlying model of what these images look like. And then these are the mean images from these distributions, so 0, 1, 2, 3, etc. So these the pixel distributions, and then the mean images from these distributions. So it's very, very simple. There's no learning actually in this at all. So but it's just illustrating how simple is not always a bad idea. And this is just an example of so this is a testing set, and then this is the training set from MNIST. So this has I think 60,000 images, and this has 10,000. So 0, 0, 1, 1, and you can see that they match up quite nicely. So there's enough there that our testing and training set populations are pretty well aligned. So what we can do is we can take a testing image, so any of the 10,000 testing images, and then compare it to the mean of each of the training images. So for these, we have our distribution of the zeros and the ones. We can just take any given instance and see how similar is it to any of these 10 digits, and then we can compute the maximum similarity. So is xj more similar to 0, 1, 2, 3 to 9, and then we just simply take the maximum similarity score and take that as our output of our model. So as I said, there's no learning in this. It's very, very simple, but it's just to kind of illustrate that a very, very simple model can give you relatively good performance. And so looking at that with different similarity metrics, so looking at correlation similarity or cosine similarity, or Euclidean or Minkowski or Spearman, this is the class accuracy and the runtime for those. So this is just to illustrate that you can get some very high accuracies in no time at all, really, on a very standard computer, on a laptop, I think, even. So there are some cases that obviously don't work very well, but a good performance comes out of a very simple, stupid model. And if we added some learning into this, then perhaps this could be improved, and then maybe some combinations of these different models. So we don't have to start with the most complex model that is available. Kind of going back to simple models can help, but this is task dependent, and this task is simpler compared to some other tasks that we have seen. So this might not translate perfectly well to those more complex tasks, but it illustrates the point of complexity is not always the answer. So now I'm going to talk a little bit about some of the tools you can use to probe your models and find out what they're doing. So there's a very interesting tool called Lime, which is introduced in this paper to help the explainability of models. So you given your original data set X, it gives you you can extract a binary vector of what they call superpixels to give you regions of the image that are associated with a given label, and you try to obtain a model from a set of models that satisfies this criterion. So you want to minimize the unfaithfulness, as they call it, of the explanation. So you want it to be a good model explaining your your data, your outcome, that factors in the locality of the pixels, so that you end up with these regions rather than kind of sparse pixels everywhere, but also trying to minimize the complexity of the model, because the more complex it is, the harder it is to understand. And the authors of this paper were quite clear on having explainable models that are not so complex, so humans can better understand them. And this figure kind of nicely illustrates that you have this image of a dog playing a guitar, but then it explains what aspects of what features of the image gave rise to it, saying this is an electric guitar, this is an acoustic guitar, and this is a Labrador. So this is quite useful to understand why we're getting certain outcomes from our models. And yeah, and so this, you can use this for looking at when models are perhaps not performing very well. So where you have misclassification here, you can find, so this was a case where a husky was classified as a wolf, and actually looking at the explanation from this line model, none of the features that give rise to this label actually relate to the thing of interest. So is a good way to identify these issues here. Likewise, you can add positive and negative cases. So why is this image a cat? So it is a cat because of this green region that is the cat, but it's also not a cat because it's a dog. So there's quite nice uses for these kind of more maybe complex images where this is no longer an image of a cat, it's an image of a cat and a dog. And then these regions have magnitude as well. So another metrology concept is trustworthiness and calibration. So this was kind of mentioned a little bit in Marcelo's talk this morning in terms of how reliable were these probabilities. So you can often see an image given a class and then a probability associated with that, but are these values actually meaningful in any case? And so we can look at these reliability or calibration curves to see how close they follow this this perfect line, and in cases where they don't, there are ways we can correct these using these different kind of scaling or regression tools. So to try and move this back to a better to calibrate these probabilities. So this is a very nice paper that kind of summarizes this well. So one method is plat scaling, where you you fit a sigmoid and you fit these parameters A and B using a maximum likelihood estimator to try and push the curve back to this diagonal line. And this works quite well for any kind of S-shaped curve, any kind of sigmoid-based curve, to recalibrate your data. Isotonic regression is given by here. So you find a mapping from your calibration point, your probability to the calibrated probability by solving this task using the PAV algorithm. So this is a lot more powerful, but it can be prone to overfitting more so than plat scaling. So you need more data for this. So in cases where you don't have as much data, this is maybe not so useful. And both of these you need to split your data testing and training as you would for normal classification tasks. So this is a nice way to, a nice thing to add on top of your model, is a similar way to Lime to better understand and improve it. And here are some examples where you have the uncalibrated calibration curves, and you can see that you have these very off diagonal, these S-shaped curves, and with these plat scaling or isotonic regression, you can bring these much closer to the diagonal, so there can be much more reliable probabilities in this case, and so we can have much more confidence and trustworthiness in the outputs of these models. And this is really critical for any kind of decision-making process. So things like healthcare, where you want to take a probability and a confidence. So when the model says I'm 99% confident, or this is 99% probably to be this this class or this class. You want to have confidence in that, and that not just be a number. So these kind of tools are going to be very important in those kind of applications. So now I'm going to move on a bit to some of the work I'm doing with autoencoders and applying that, and how trying to use some of these concepts in the machine learning task. So this is also Marcelo's talk this morning, talking a bit about variational autoencoders. Here I'm going to talk about stack sparse autoencoders. So this doesn't have assumption of or requirement to make these Gaussian in this low dimensional space. So the only assumption is that given an input set of data, there exists an encoding that can be learned, that can be decoded to reconstruct your input data. Using this encoding function, so your activation function sigma, which can be a linear or a sigmoid or a tangent or a relay or something like this. I use sigmoid in the following slides. For this, a lot of the tasks I use, I find it is better for those given tasks, but happy to discuss that more with people afterwards. So this mapping to this Z space, this encoded space, and then decoded back to the output data, and the learning task here. So you can learn these in a layer-wise manner using gradient descent to minimize this difference between your input and your output by solving this. And so that's nice and easy. Often you would add regularization here to enhance the model. So here, so L2 regularization to reduce the complexity of your weight matrix and better condition your model. And also this this term here for the sparsity. So this is the average activation of each neuron in your model. And if you have a low activation, that means your neurons are responding only to very specific features within your data. And so that's very good for what I found for sparse data, where you only want the neurons to fire for very, very specific instances. Where you have very, very non-sparse data, this isn't always very low. So it tends to be something you have to tune a bit. And so this is essentially a chaos divergence between the average activation of your nodes, your hidden neurons, and a predetermined one. So how active you want them to be, and that's a parameter you tune based on your data. And typically, I've found for non-sparse data, this maybe needs to be a bit higher than for very sparse data. You can have it quite low. And yeah, so this is trained in a nice unsupervised way, and to give you this encoded space. And so here are some examples of how we've used it. So this is an example of some mass spectrometry imaging data. So this is a high dimension hyperspectral image where every pixel is made up of a mass spectrum. So which tends to be fairly sparse data. The images typically have tens of thousands to tens of millions of pixels. So there's not really a shortage of samples for training. And so in many cases you can do a lot of subsampling on this if you have computational limitations. Yeah, again, decoding to your original data. So typically what I would use this for is to primarily initially for a visualization task, so reducing down to 3 dimensions, and then having one of my dimensions as a red channel, another one as a green, another one as a blue, and this way you can visualize this image. So where this would have tens of thousands of images here, which this is kind of cycling through and showing you these different components, some of which will be highly correlated, some of which will be very very localized. So this is a nice way of viewing this entire data set in one single image, where the same colors represent the same components, same features. which in this case are the master charge values measured. So it's a nice way to summarize the image, and as we learn, as the network is trained, you start from a random initialization, and then you end up with these clusters forming, and then these segments from these images being formed. So and this is a mouse brain, and this corresponds quite nicely to the known anatomy of a mouse brain. So this is great for visualization, but we can also use this space, or even something that's not 3. We can use a higher dimension than 3 if we like, for classification. And so the advantage of doing this versus, say, taking the 4-dimensional data is this might have tens of thousands of inputs, and as you can see from here, a lot of it is maybe very, very low. There's low intensity. There's often a lot of sparsity in this data, so it's easier to solve a problem with 3 features than 10,000. It's much more computationally efficient to do this problem than this problem. So what we did in this paper was we took several kind of common classification algorithms, so kind of forest, SVM, Bayesian Bayes nearest neighbors, and a sigmoid, and lots of different evaluation metrics, so sensitivity, specificity, F measure, to look at the differences in true positives, true negatives, false positives, false negatives, and then look at these in these radial plots, so where we have 0 to 1 in all these directions, and then the scores for the accuracy, precision, etc., for the different models. So here's K nearest neighbors, LDA, and these are 2 SVMs, so we have a linear kernel and a Gaussian kernel. The red here is a high, sorry, these colors are the wrong way around. The red here is the high dimensional data, and the blue is the low dimensional data. Apologies, these should be the other way around. So this is a measure of how overfitting it is. So these are not the raw scores. This is how good the testing score is compared to the training score. So 1 means your testing performance is the same as your training performance, so your classifier is as good as it can be for that problem, and then less than 1 means you're overfitting. So you can see here that they're using the higher dimensional data. The area of this, all of these points tend to be lower, so you've overfitted your model based on these metrics, and that's kind of across all of them. So we tried many more models than these 4, but it was a fairly universal finding. Autoencoders, you can also use them for, I say towards traceability, because there's still a lot more to do, but because this is a stacked sparse model, once you've trained it, the network weights are fixed. So it's if you continually apply it, you get the same result. So it's nice and deterministic, and you can take your input data, embed it, and then you can actually then decode it and look at what features are driving the clustering or the classification if you're doing that task of your data. So here we took some medical records. So this is from the Royal College of General Practitioners Research and Surveillance Centre. So they've got practices all around the UK who send their medical records to this centre, and these contain lots of anonymized information. This extract was a very, very small one of just 11,000 records relating to flu. So it just had age, gender, and some information about the condition. So the type of flu, some clinical coding systems. We converted these to numerical strings based on a kind of ASCII encoding of all the individual inputs, and then encoded that into a low dimensional space. There's 3 dimensions, and we get this nice cluster map here. But because this is fixed for once it's trained, we can then isolate these clusters and then decode them, or decode representations from them, to see what features are driving them. And in this case, we can uniquely describe all of these by 3 of these features in this data. So all of these clusters can be uniquely identified by specific inputs, specific fields in the inputs. And we can also look at the distribution of other things. So this is looking at the distribution of gender in these different clusters. And this is something called episode time, which is relating to the recording of it. But interestingly, you can use this to look at different biases potentially in the data. So because this is related to influenza, we wouldn't expect to see a particular difference between men and women. So it's interesting it's good to see that there's not a clear difference across the clusters. There are some kind of ones that maybe are a bit more leaning towards one gender over another, but I think that's a sample size issue rather than a bias issue. I'm idea of time. So this is.
Yes, if I could just ask you to sort of tie up in the next few minutes so that we've got some time for questions.
Yeah, sure.
Thank you.
Sure. I've only got a handful of slides left. So this is just another example of training it on one subset of a larger data set. So here's some hyperspectral images of faces, and here's some mass spectrometry images, and then applying it to a larger cohort of data sets and seeing very, very comparable results across them. So you can apply this to new data sets. This is probably the last one I'll spend any time on, and then I'll conclude. So another thing that's nice about these autoencoders is you can look at things like, is the cluster size meaningful, and how can I look at the uncertainty, or can we get anything that gives us a kind of proxy for that in this space? So taking these as kind of probability distributions, we can look at the Shannon entropy of these to get an idea of how disordered these clusters are. But we can also do this for the high dimensional data. So we can calculate the entropy for the inputs, even if they're mixed type. We can just do it for the different fields and then sum that together. And what was interesting is that if we take this low dimensional cluster entropy, and then we take the entropy from the high dimensional data, so for the different fields we compute the different data types independently and then sum that entropy together, there's a direct correlation. So the bigger the cluster here, the more disordered the high dimensional data is. So this is maintaining the characteristics of the data in the low dimensional space. So it's a nice low dimensional representation of it's not just a nice visualization, it's capturing those features. And you can apply that to other problems. So we've looked at biomarker data, weather data, this is patient demographics, or even metadata around imaging, and you can get these very nice clusters forming out here, or even these continuous curves here. So this is weather. So this, over the course of 5 years in 10-minute intervals, weather is fairly continuous, or at least this data was. So that is essentially all I had. There's just some brief conclusions now. So I've shown a few examples of how traditional metrology can be used in machine learning, and some references for those, and how and why we should consider models and data separately and together when we evaluate them. The calibration and explainability and how that can be used. Traceability is still an area we need to look at, and how we can compare low and high dimensional data, and then a bit on autoencoders. So the last slide is these acknowledgements. So I've got a lot of colleagues at NPR I'd like to thank, collaborators and at Surrey and externally, and some students. And I'd like to thank the organising committee for the invitation to speak, and thanks everyone for listening, and I'll be happy to answer any questions.